Okay, so the first thing is I put up the first weekly assignment. I was a little late on getting that up, but there's a weekly assignment up now that's due next Monday. I mean, that's possible, but somewhere around there. And so yeah, there's no solutions for that. That's really, practically speaking, that's the difference between that and the daily assignments. You can talk to each other about it, but you have to turn in work that you do yourself. You can work with other people to figure stuff out. I don't think you'll find it to be too much different difficulty-wise than the daily assignments, you know. And then, that's, I'll grade that more carefully, and that'll be like a bigger, chunkier grade. You know, that's all in the syllabus. Anybody have any homework questions before I get into new stuff? Okay. So we're doing the second law of thermodynamics. And that can be expressed in three different ways, you know, three different statements that are all equivalent. The first one is the Clausius statement. That's the one that's really intuitive. It's not really useful for calculations or anything, but it's useful for reminding yourself what all this other stuff is kind of about. And it just says that heat can't be transferred spontaneously
So when you find a stopping point, I remembered I did have one homework question.
Okay. From a cooler to a hotter body. So that's what this is all about. And one of the things that the second law of thermodynamics is useful for is we'll be able to do calculations about the direction of processes. You can't do that with the first law of thermodynamics, but you can see that there's directionality implied in the Clausius statement. You know, if heat is moving from hotter to cooler, then time is going forward. You know. Then the second statement is the Kelvin-Planck statement. And that says for any system, for any cycle, a system in contact with one thermal reservoir cannot produce any network. So mathematically, you can write this as for a system with one thermal reservoir, the work done by the cycle is less than or equal to 0. Okay. So that thermal reservoir you can think of as like the boiler. That's the heat you're adding to like a power cycle. What?
Like so far, this lecture word for word is what?
Yeah, I'm just summarizing.
Oh, okay.
I'm not going to do this for too long, but we're getting into new stuff. Okay. I could see you weren't listening, so I'm going to say it all again. And then the third And then the third one, the one that's really like mathematically going to be the most useful for us, is the entropy statement. And that says that for any process, the entropy of the system plus the entropy of the surroundings is greater than or equal to, no, these have to be the changes in entropy, sorry, is greater than or equal to 0. So entropy is going up in the universe every process. And we haven't defined entropy yet, but today we'll do that. Okay, so we've talked a little bit about the Kelvin-Planck statement. We talked about how you could use that to get to these measures of efficiency for power cycles, heat pumps, and refrigeration cycles. So now we're going to talk about the sort of intermediate step to defining entropy. And that is what's called the Clausius inequality. And the Clausius inequality says that for a cycle, if you take all of the heat that's transferred into your system divided by the temperature where that's transferred in, going around the whole boundary, that's what that B is, go around the boundary of your system, and at every location, take the heat that's being transferred in and divide it by the temperature where it's being transferred in. This is less than or equal to 0. This is true for any cycle, you know, not some kind of ideal cycle. This is true always. And the equality, you know, this is equal to 0 if this is a reversible process. This is going to look familiar when we get to, you know, this is related to how you calculate entropy or how you define entropy. All right, there are a couple things I want you to keep in mind about the Clausius inequality. So first, the Clausius inequality looks similar to the Kelvin-Planck statement. So the Kelvin-Planck statement says that if you have one reservoir, one thermal reservoir, one boiler, the work done over any cycle is less than or equal to 0. This is true for any cycle. And 0 is only, you know, the equality to 0 is only if it's a reversible cycle. So notice, it's the inequality is there, the less than 0 is there. It can be any cycle. The equality is only if it's a reversible cycle. Those similarities are there because I'm not going to do the derivation, but it's not a real long derivation to go from the Kelvin-Planck statement to the Clausius inequality. So that similarity is because the Clausius inequality is derived from the Kelvin-Planck statement. Second, just to sort of have an intuitive sense of this, because it's not immediately super intuitive, that statement. But let's think about this in a process, in a cycle that's just super simple and see how it works, how it has to work. So we're not talking about like a power cycle or anything like that, but just to have intuition, or let's say to make sense out of the Clausius inequality. Imagine a system that first brings in heat from a hot reservoir. And then second, ejects, loses heat at a cold reservoir. So I'm just going to put numbers on all this stuff. So let's say that up here we have a hot reservoir that's at a temperature of 300 Kelvin. Okay. And let's say that an amount of heat of, whatever, I'm just totally making these up, but 1,000 joules of heat is brought into the system from that hot reservoir. And then to make it a cycle, since nothing else is going on in the second step, we have to eject that 1,000 joules of energy through heat to, let's say this one is 200 Kelvin. And so what does this notation mean for that? I mean, it just means that throughout the whole cycle, at everywhere around the boundary where there's heat transfer, you have to take that heat, divide it by the temperature where it's transferred, add it all up, and that has to be less than or equal to 0. So what we have here is heat coming into our system that's 1,000 joules divided by 300 Kelvin. Okay, that's using the sign convention that we've used for the first law and everything. That's positive. And then the heat you're losing is negative. So minus 1,000 joules divided by 200 Kelvin. Now, I couldn't have the 300, the 300 bottom and the 200 at the top because of the direction of flow of energy. You know what I mean? So you have to have that higher temperature where the heat's coming into your system. And because of the denominators, then you can see that, this is equal to 1,000 joules divided by, well, what is it? So make that 600. So yeah, minus 1,000 joules divided by 600 K. Which is what, 1.6 repeating joules per Kelvin, I think. Negative. Okay, so because you can't get the heat to transfer spontaneously from the low temperature to the high temperature, it has to work out to be negative like this. If it was a reversible system, you'd be transferring those heats over infinitesimal temperature gradients, and so you would have the same temperature in the denominators of both, and you'd get 0. Okay, but you can't ever get the heat just to transfer the other way, and so you can't ever get positive. So it has to be negative like this. Or 0 if, perfectly reversible. And then the last thing, maybe the most important thing about this to remember, so why do we even care about this inequality? I mean, it doesn't really come up on its own that much, but it's where the calculation of entropy comes from. So from the Clausius inequality comes the definition of entropy. And it's defined in terms of a change. And it's equal to the integral from state 1 to state 2 of dq over t for an internally reversible system. Okay, so that means that the change in entropy, so every internally reversible system would have the same answer for this delta S. And so this is a fixed defined amount between state 1 and state 2. Entropy is a property that you can look up in tables because of that. And so yeah, we'll do some things where you're looking up entropy values in tables. I'll talk about some ways that you can calculate changes in entropy using other properties for like ideal gas law and incompressible substances and stuff like that. Okay, so those are the 3 things to remember about the Clausius inequality, the 3 reasons that it's useful. Let me do this example problem, sort of a conceptual, proofy kind of example problem. But let's say that we have a reversible and an irreversible power cycle. For both, let's say that we discharge an amount of heat QC to a cold reservoir at temperature TC. And receive an amount of heat QH from the hot reservoir. The difference is, since one of these is reversible and one is not reversible, the hot reservoir has to be at different temperatures. They're going to be at different temperatures. So for the reversible, we're going to call the hot reservoir temperature TH. And for the irreversible, we're going to call the temperature TC. Not TC, I'm sorry. That would be crazy. TH prime. Okay, so based on what you know about like the efficiencies of these things, which of those two is going to be a higher temperature? So since the reversible one is more efficient, you don't need as high a temperature to get the same heat transfer. Okay, so with an irreversible one, it's all rusty. You have all these sources of inefficiencies. You have to really blast that furnace to get the same amount of energy out of it. Okay, so we expect that TH for the irreversible one to be a higher temperature. Okay, so that's what we want to show. Show that TH prime is greater than TH. Okay, so for the reversible one, so we have this temperature TH, and the heat coming in is QH. And then we have this cold reservoir TC, and QC is going out. And for the irreversible one, we have a temperature TH prime. It's still that same amount of heat going out, so this is QH. And then to the cold reservoir TC, we have an amount of heat QC. Okay, so for the reversible one, I'm just going to keep working in the columns so you can see the two next to each other. Based on the Clausius inequality, so if we're going to use the Clausius inequality for this, what's the fact that we're going to use here to do this proof? Yeah, so for this one, we're going to use the equality. This one, we're going to use the inequality. Exactly. So we have, for the reversible one, QH over TH minus QC over TC is equal to 0. And so QH over TH is equal to QC over TC. For the irreversible one, we have QH over TC prime minus QC over TC is less than 0. TH, yes, TH prime. I'm only going to make that mistake twice in this proof. So now that we've calculated this equality here, we can substitute the QH over TH here, and you get that QH over TH prime is less than QH over TH. These are all positive, so multiply stuff around and you get that TH prime, well, let me keep it in the same direction. TH is less than TH prime. Okay. You could do the same thing with, you could do the same proof to show that if everything else is the same, except the temperatures of the cold reservoir, you would need a colder cold reservoir for the irreversible cycle than for the reversible. Okay, so that has to do with, that's all related to how efficient the engine is.
Is that always the case where it is more efficient than the temperature of the device?
Yeah. Actually, you can just look back at the definitions of efficiency of like power cycle performance and stuff, and you can see those relationships. Okay, so now we're going to finally talk about entropy. So consider any process well, that's redundant. Consider, undergoing any process. Consider any process from state 1 to state 2. Then the change in entropy from the beginning to the end of that process is S2 minus S1. And it's equal to the integral from state 1 to state 2 of the heat transferred divided by the temperature where the heat is transferred that would occur for an internally reversible process. Okay, so no matter what process you're going through, you have the same entropy at the beginning and end, but that entropy is defined as what would be produced here by an internally reversible cycle. Okay. Notice that if you calculated the integral of dq over t for an actual cycle, you wouldn't get the change in entropy. Okay. You get something smaller. Okay, something more negative. So the definition of entropy uses this idea of an internally reversible process, but we can use it to evaluate any 2 states. It's an extensive property with units of energy per temperature. Which means that in SI units, it has units of joules per Kelvin. JK. I'm just kidding about all this stuff. And tables list the specific entropy and that's, lowercase s, and that's the entropy divided by the mass. Okay, any questions about that definition of entropy? So the idea is, the definition requires this idea of internally reversible, but the things you get then for the beginning and ending states are just true of those states. They don't have anything to do with how you got there. And so you can use entropy to evaluate any 2 states, no matter how you get from one place to another. Yeah, question? Well, it would be, so if you look at this proof that we just went through, wait, is that the one? No, look at this this sort of intuitive thing that I said, so if this was, think of this as it's using that integral that's in entropy, you know. So this is like calculating that integral. This is a real cycle, you know. You have to go from that higher temperature to that lower temperature. That means you have to end up with something negative. Okay. If it's reversible, then you end up with something zero. It's bigger. Yeah. We would prefer to be able to calculate changes in entropy without measuring heat transfer. It's a difficult thing to measure. So let's say we'd like to be able to calculate this change in entropy without measuring Q. And so the way that we can do that is by combining let's see, so it's combining the definition of entropy with the first law. And you get the TDS equations. So there are two of these. And you can write these two equations in the extensive form or the intensive form. The intensive is going to be more useful to us. The extensive form looks like this. Temperature times ds is equal to du plus p dv. And TDS is equal to dH minus V dP. This is the one that's going to be more useful to us. The intensive versions of these, say T d little s are equal to d little u plus P d little v. And T d little s is equal to d little h minus little v dp. And from these, in special cases, you can integrate to come up with relationships between the change in entropy and the change in these other properties. So let's say in some cases, you can integrate to relate ds, or delta s really is what we want when you integrate, to delta u, delta h, and delta p, and delta t. T is in there too. Why would we want to do that integral? It looks like sort of a mess. Like if the entropy is given in our tables, like why would we want to mess with this anyways? Like notice it's doing the exact same stuff the tables are doing. But it's the same reason that we have the ideal gas law, and we had the incompressible simplification. There are times that we don't have tables for our specific mixture, or our tables don't go to the values that we want. And so these are cases where, the tables aren't there. We can still calculate some things. Also, notice that you might think this tells us, that du plus pdv is equal to dh minus vdp. Is that something new? Is that something we can use? It's not really. Because if you just think of the definition of H is equal to U plus PV, then the chain rule says DH is equal to DU plus dP times V plus VdP, and that rearranges into that form. I did VdP. This one should be PdV. I'm just doing the chain rule there. So dH minus VdP is equal to du plus PdV. Okay. So the TDS equations are not useful at all for relationships between U and V and H. They're only useful for trying to find changes in entropy. So only use the TDS equations to find changes in entropy. Any questions about that? So this is important. So when can you use, I think this is really the thing that you have to ask yourself all the time with all of these equations in thermodynamics, like, what does this apply for? Is this an idealization? Is this like your real states? The TDS equations are valid for any process. That's because if you look at them, they're just relationships between properties. And so if you're relating properties, the way you get from one state to another state shouldn't matter. Okay, so now, in general, generally, you can't just take any kind of material, any kind of process, and figure out a way to do that integral. But if you know some things, some ways to simplify your process, if you know the functional form that something's taking as it moves, or as the process takes place, or especially if you have a case where pressure is constant or volume is constant or something like that, and things disappear from the integral, then you can do this. So let's do an example like that. So let's say that water goes from a saturated liquid to a saturated vapor. As pressure stays constant at 1 bar. And so we're going to calculate the change in specific entropy we're going to do it twice because with these simplifications, we can use either one of the TDS equations. Normally, you're just choosing one or the other that works, but we're going to do it, using each TDS equation in this case. Okay, so what's going on so it starts as a saturated liquid. The pressure stays constant as it turns to a saturated vapor. So this is just the phase change going on. So what do we know about the temperature?
Oh, it's constant.
It's constant, yeah. So the change in temperature is 0. The change in pressure is 0. So first I'll start with this one. TDS is equal to du plus P dV. So ds is equal to 1 over T du plus P over T dV. So now integrate everything, and you get that the change in entropy is equal to 1 over the temperature. That's something we can look up in the table. Times the integral of du from state 1 to state 2. Plus pressure over temperature, those are both constants, times the integral from state 1 to state 2 of dV. And so the change in entropy is 1 over the temperature times, U2 minus U1 plus the pressure over the temperature times the quantity specific volume 2 minus specific volume 1. So now look up the saturation temperature at 1 bar. And U1, U2, V1, and V2. And you get 1 over the saturation temperature at that pressure is 372.78. Times the specific internal energy at state 2. If you look that up, you get 2506.1 times 10 to the third. I'm doing it all in SI units. Minus the internal energy at state 1, which is 417.3 times 10 to the third. And then plus the pressure. It's constant, so it's just 1 bar. Divided by that temperature again, 372.78. Times the quantity. Now we're looking up the specific volumes. So 1.694 minus 1.0432 times 10 to the minus third. You have to put a lot of energy into any material, into water in this case, to make it go from a liquid to a gas. So you can see that big change in internal energy, and you can see the big change in volume that happens. And if you calculate this, you get a change in specific entropy of 6057 joules per kilogram times Kelvin. And that's not an approximation, that's exact, you know. So to do this calculation, I mean, we still use the tables. So we're basically just acting as if the tables didn't have entropy in them. But now if you just look at the entropy difference in the table, it's exactly that. Okay, so now I'm going to give you guys a minute to try to work through this one. This is the kind of problem that you'll have to do with these TDS equations. So now the second TDS equation says TDS is equal to dH minus V dP. Okay, so this goes away because there's no change in pressure. And so ds is equal to 1 over T dH. And T is constant also, so we can just integrate this and this. And we get that the change in entropy is equal to 1 over T times H2 minus H1. So that's 1 over, is that same temperature we had before, 372.78 Kelvin. Look up the two enthalpies, and you get 2675.5 times 10 to the third minus 417.46 times 10 to the third. And so the change in entropy is same thing again, 6057 joules per kilogram Kelvin. And again, that's an exact value. And again, that doesn't depend on the process that it follows or anything. That's just what happens if you go from this one state to another state.
One last quick question.
Yeah.
So then for the table values, I assume that you don't have a direct means of measuring entropy. They calculated the table values?
That's right.
Okay.
Yep, they calculated them. And yes. Well, let's stop there, and I can answer your homework question.
Oh, yeah. It was just a quick one about the last assignment.
And so, yeah, next time we'll get into this for incompressible and ideal gases.
So 3 lists the possibility or lists steady state explicitly.
Mm-hmm.
2 doesn't, but I realized when going through, you know how we have the efficiency equation to show whether or not it's reversible?
Yeah.
So I have the cycle being possible by the efficiency equation for C.
Mm-hmm.
Looking at the energy, you know, what's coming from the hot reservoir and then the work that you're getting out along with the cold reservoir. That doesn't add up.
Yes, actually, that is. So the answer is it's not possible because of that.
Okay. Yeah.
Right.
So anytime we do look for these, we should consider conservation of energy.
That's right. That's the idea with that.
I wasn't sure if there was
it's just about like trying to keep track of all the requirements that have to be. Yeah, that's right.
Okay, that makes sense then. I wasn't sure if there's a case, you know, heat cycles where, well, I mean,
something else is happening, but it doesn't.
Yeah,
no. You're assuming that all of the, however the heat is transferred or whatever, that's included in that.
Okay, yeah. So by energy conservation.
Exactly.
Okay, got it. That answers that.
Okay, any other questions? All right, sounds good.